this microphone working? Yep, okay. So my name is Ian Mitchell. I'm a professor in the computer science department, and it's my great pleasure to introduce today's distinguished lecture speaker. I first met Claire when I was a master's student in computer science at this department. I got to go to a conference, and there was a woman presenting at that conference in Notre Dame who got up, gave a presentation, sat back down, and I never heard a peep out of her the rest of the time. And it turns out that she had a horrendous cold that weekend and just was feeling miserable and still managed to go to Notre Dame and give a presentation. As it turns out, when I went to Stanford a couple years later, who should show up as an assistant professor but Claire Tomlin? And I managed to convince her to take me on as a student and completed my doctorate there at Stanford. Claire has since moved to Berkeley. I have one story I'd like to tell you because it may have relevance to today's talk. When I was finishing up in 2002, I got married and then immediately went off to France with Claire and one of my friends, Alex. My wife likes to say that I took my honeymoon with Claire and Alex, not with her. We went and gave a presentation at Dassault, which is an aerospace company there. And Alex and Claire carefully coached us the night before, went through our slide decks, made sure that we had lots of slides that were very industry relevant. We each had, I think, 20 or 25 slides. And she said, we've got an hour to present to these folks. I'm going to take about 10 minutes to give an overview of the lab. And then you guys can each have about 20 minutes to present your slides. And so we got to Dassault the next day, went through the security checks, got to the conference room. Claire opened up her laptop and opened up a slide deck with 90 slides. So about 45 minutes later, Claire wrapped up and handed it over to me and Alex. And we gave extremely short versions of our talks. But the good news was that Dassault really liked it all, and we got to go to a wonderful lunch afterwards. Claire always gives amazing talks, and let's say covers a lot of things in a very short period of time. So Claire is now a full professor at the University of Berkeley in electrical engineering and computer science. She is a fellow of the IEEE and the AIMBE, which is a biomedical association in the United States. And she is a certified genius, winner of the 2006 MacArthur Fellowship. So I will turn it over to Claire now. Thank you.
Thank you, Ian, for that really nice introduction. I'm going to try to finish, because Ian told me, I think based on the 90 slides, that I have to finish by 4:20, not to go past 4:30 because people will start to leave. He said it very earnestly, so I think that I have my goal here of time. Ian started a tradition in our lab. I think he started many traditions. One was is really the focus of this research that I'm continuing to present and continues to grow and develop. And it's something that, I kind of started it as a PhD student, but Ian, as the first PhD student in my group, worked on computational approaches to some of the methods that I'm going to talk about today. He also started a tradition of really good food at group meetings and thesis defenses. So, combining really good sushi with Krispy Kreme donuts, which were the big thing at the time, that sort of started another very important tradition that perhaps some of you recognize here. So I'm going to talk about a project that has been going on for quite a long time. It's in safety and safety for control systems. But I'm going to focus a little bit on some of the work we've been doing more recently in how to integrate machine learning into safety-based control. And throughout, I'll talk about some of the applications we've been working on and some of the driving applications and some of the kind of robotics applications that we have in our group. So I'd like to also thank you for inviting me for this lecture, in particular Ian and Mark and Holly for this gracious invitation. I'm going to start by defining the kind of model we've been working with for the past several years. And that's that of a hybrid system. It's called hybrid because it combines two different types of dynamics. Discrete state dynamics. You see that in this representation of a finite state machine. With continuous state dynamics, you see that in these representations of differential equations associated to each discrete state. The idea is to try to capture a complex control system through its modes of behavior. Each mode may be modeled with some set of differential equations, and then as you switch modes because of control or because of just the fundamental physics of the system, the dynamics change. So you get different differential equations, for example, in each mode. So you have a neat kind of interplay between continuous evolution and discrete jumps of the state. And so this is kind of a modeling paradigm we've been working with. It's been very useful in one of the key applications we've been working with now really for the past 25 years, which is that of modeling aircraft and air traffic control. This is just zooming into a particular scenario. The aircraft are, of course, larger than they would be in real life, but looking at a typical scenario that an air traffic controller would deal with over and over again, which is that of ensuring that the aircraft stay separated from each other. So even if they're coming together and merging into a route, taking them into a busy airport, they have to be sequenced in such a way that they maintain separation. And so one of the models that we've built has these sequences of discrete modes based on the kind of control that is being used by the controller and that we subsequently tried to identify from data and then automate in simulation form to validate this model of air traffic, of an aircraft under air traffic control. So you see these different modes. Most of the time it's in this average speed mode, flying at the velocity that's optimal for the altitude it's flying in. But then controllers can do things like speed it up a little bit, slow it down by a little bit. If it's more drastic, it will typically put it in a detour or a shortcut away from its route to, say, avoid collision between aircraft. And I mean, it's really a human-centered control system. The controllers tend to, the human air traffic controllers, they tend to group aircraft together by potential conflict. So they, the structure of the airspace kind of admits this fairly straightforward control structure where they'll try to line up aircraft along a single route so they can basically treat that group of aircraft flying at the same velocity as a single aircraft, and then they really have to focus their attention on potential conflicts or potential conflicts that may happen a little bit further into the future. So the goal in the control problem, and when I'm just saying a few words about this, but really thinking about providing automation and advisory tools to air traffic control is typically the controller wants to provide a small set of control actions, try to keep it on its desired route and deviate it as infrequently as possible. But also grouping aircraft together by potential conflict. So there's a kind of hybrid system representation, both in the structure of both in the control structure as well as in the structure of how the aircraft fly through the airspace. It's becoming an even more interesting problem now, and this reflects more of our current work, in that there's a whole bunch of new potential applications of both drones in the airspace, commercial applications of drones, as well as ideas in the near future of personal mobility, so small automated vehicles that will take people from one side of a megacity to the other side. And so this represents a little bit of the drone application with NASA that we've worked on. So the questions are really, when you try to generalize the airspace and you try to allow it to adapt to these new forms of, these new types of aircraft that are flying at different altitudes or they have different traffic patterns, how do you do that? How do you maintain a kind of control structure over the space? And do we, it's still a human in the loop system, so we want to maintain some of the simplicity of representation representation. But the new systems will be much more automated, so they have to be able to adapt to new information. So there's not only like a pre-designed control, but there's very much a need for automation and data-driven. So collecting data from current sensors and adapting in real time. Hence the necessity to include machine learning. So I'm going to talk about hybrid systems. I'm going to talk about reachability, which is a tool, again, this is something that I've worked on and Ian worked on as starting this off in the group, and with some examples. And then I'm going to switch over to talking about incorporating machine learning. Okay, so the core, of different things we work on, this is sort of one core tool. The core computation around these problems has been that of a reachable set. And it can be a forwards reachable set or a backwards reachable set. It's very intuitive. It's the set of states that you can get to. So the set of states, the set of configurations of the system. Suppose you have some well-defined initial set characterizing under the control possibilities or under the actions of the environment where the system could get to. If you have an uncertain environment, that set becomes more and more uncertain. Here I've represented it in terms of the backwards reachable set. So suppose that you have a set of states. Let's say this is a set that you don't want the system to get into. So it's some unsafe configuration, like 2 aircraft in a set of aircraft in air traffic control losing separation, coming closer than the requisite distance. So here, if you knew the dynamics of the system, so here's just a simple representation of the dynamics of the system. Differential equation, the state might be the combined state of the aircraft in the system, or the 2 aircraft that you're looking at, their velocities, whatever kind of model you want. Control inputs, uncertainties, which we model as disturbance inputs that you can't control, but you have some knowledge on their bounds. Then what this set represents is the set of all states which, for all possible control actions, there's some uncertainty, some disturbances in the system, which under the dynamics of the system could drive the system to this set in t time units. So it's parametrized by t. So there's a couple of things to say here. First of all, the details is in computing this, and it's generally hard to do this in high dimensions. And a lot of our work recently has focused on how to compute these sets in high dimensions. But it's also got this interesting component of control to it. So there are actuators in the system. You are able to control them, and you have control over that as the designer, as the human interacting with the system. But there are things that you must control against, and you don't necessarily know what they're going to do. So typically, in this perspective, where it's typically a safety critical system, so we'd like to be conservative, we assume that those disturbances are doing their worst behavior. And so we use the framework of game theory. We want to compute the best possible control for the worst possible disturbance, and then characterize under that control the states that still wouldn't, that you still could not escape entering unsafety, say in this example. And it can be quite conservative if you don't really know much about your disturbance. But the more you know about your disturbance, the less conservative, maybe the smaller that set becomes. So we did some early on some work in characterizing this and showing that you could actually compute this set and characterizing what the set was as the zero level set of a partial differential equation. And moreover, built sort of some ideas about the numerical computation of this set. So the idea is that we represent the set generally as the zero level set of a function, and then we do the manipulations on the functions. And that gives us certain nice properties. It's a lot easier to represent interesting shaped sets by level sets of functions. And it's a lot easier in some sense to do the mathematics on the functions themselves and then record what happens to the sets. So it's a level set interpretation. This is just showing a slice of a level set where the zero level set, here's the function that you started with, and then the function evolves to be some more interesting shaped function. So you could, for example, represent disconnected sets using this level set representation. The other thing that's interesting about control, and I touched on this, is that you have this nice property that if this set is controlled invariant for all t, say it doesn't, there's a point in time you backwards propagate, then it stops changing, it closes off and it doesn't change anymore. Then you have the property that any super zero level set of that, so just think about, now we're taking slices of that function, is also controlled invariant. And so a super zero level set of that can also be used to guarantee safety, for example. If you don't get into a super zero level set, you don't get into the zero level set. And the more you know about the disturbance, the less conservative that set becomes. Okay, so there still may be some set just based on the raw dynamics of the system with known disturbance. But as you get better and better knowledge of the environment, the uncertainty in the system, the less conservative you generally are. So that comes up when we talk about learning, and that'll come up a little bit later. So the set partitions the state space. You've basically taken whatever the continuous state space, and you've divided it into 3 regions. States that are safe for at least t time units, states that could become unsafe in t time units, and then the boundary states, where on this boundary here, so in these boundary states, you can remain safe by applying the control that you computed as part of that overall level set computation. Okay, so here is Ian's toolbox that he developed after coming to UBC and really developing a numerical toolbox to compute these level sets. This is just a link to that. I think it's beautifully documented, and it's also nice because you can download the code and also look at the dynamics in his examples, pull those out, plug in your own dynamics, and run with it. Okay, so this is just an example of one particularly interesting set that we were computing, and you can see it's the zero level set, or sub-zero level set, I should say, of this function. And it also has nice information for control, right? So if you're controlling the system in the state space, at each point in the state space, you not only know that you're outside the set, you get a measure of how far you are away from the set. So that's also useful. If you're getting close to unsafety, it's useful to plan for that a bit. It gives you a bit of a preview and a sense of how far you are away from violating the safety constraints. This is one of the first examples that we did. This is back when I was at Stanford. So the name is STARMAC for the Stanford Testbed of Autonomous Rotorcraft for Multi-Agent Control. This is kind of, and you can see this, right? This is before you could buy a quadrotor on every street corner. So we built these ourselves. This is back in like 2002. And we put did the onboard computers and everything. They're basically carbon fiber tubes with tube straps. Anytime they crashed, it was a pain to try to figure out, where the crack was so that we could get it working again. But here is an experiment where we've got 4 students, and each of them is controlling one of these vehicles. So they're joysticking them around. And when the vehicles come, so there's 4 vehicles, each vehicle has 3 backwards reachable sets around it relative to the 3 other vehicles in its vicinity. When a vehicle gets to the boundary of one of the reachable sets, that means it's about to violate safety, the automation on board the quadrotors takes over and guides the vehicle away outside the reachable set. So you get that control action from the computation. And then at some kind of not very well-defined point, control is given back to the human controlling it, which is not a very good user interface, but it's an example of how you might automate the safety-critical portion of this, not how you do the transfer. You can also use this kind of computation for the reverse problem, not just avoiding sets, but reaching sets. So here is a desired set that you want to get to. This is the, backwards reachable set. It just looks the same in the stylistic view. But it's essentially the same computation. The min and max, their roles are changed. Now the control is trying to drive the system to a desired set despite the worst case disturbance. And so the kind of computation is the same. We typically call these sets the capture basin. So the set of states for which you're guaranteed to reach a desired set despite disturbances that may be pushing you outside of that. And then you can piece these together. So for hybrid systems, you're often faced with mode switching. So you want to figure out, for example, how to get to a target set in one mode, where to get to that mode, you've gone through, say, a sequence of other modes. So you have to get to the capture basin of the final mode and then switch over to the dynamics of the final mode. So the control law now is both a continuous control as well as a switching-based control once you get to that. And at the same, you can couple that target reaching with avoiding unsafe configurations. And so we call these sets, that sort of blue set union is what we would call the reach-avoid set, the set of states for which you can reach targets and avoid state constraints, safety state constraints or other at the same time. Okay, so let me spend a few minutes talking about cursive dimensionality. I've shown you some stylized pictures and one fairly simple example. The big question here is how to compute these sets. You have to solve a partial differential equation. And that solving for the game solution, the input and the disturbance, is typically not hard because you're doing those over bounded intervals. What is hard in general, computationally, is propagating those sets backwards in time. Because the sets, in 2 dimensions and 3 dimensions, it's easy and can be done in real time. As you get to higher and higher dimensions, it becomes hard because, in general, you're gridding up the state space. And your computation then becomes exponential in the dimension of the continuous state. So there's a community of people from kind of the control and CS verification, computer-aided verification communities working on these problems of dealing with high dimensions. And I've listed some of the different strategies that people have used for basically dealing with high dimensions. And maybe the most practical strategy is the first one, which is just to actually look at the problem itself, the physical problem, and impose some practical constraints so that you don't run into high dimensional problems. So with this NASA problem that I was telling you about, the UAV, so basically an air traffic system for unmanned air vehicles. The collision avoidance problem, you could imagine, could become very hairy very quickly if you have lots of UAVs and they're all flying around the same area. So it's clear that, if they're going to fly in the airspace, there needs to be some structure. What sort of structure do you pull out of the existing air traffic control system, or how do you design a new structure? So we proposed this idea of platooning UAVs. So a similar idea had been proposed back in the late 80s and early 90s for the California Path project of platooning vehicles on the inner lane of California's highways. What that does is there's a highway structure, so it basically simplifies the collision avoidance problem. You only really have to worry about the vehicle in front of you or the vehicle behind. And so a platoon is basically defined as vehicles flying along a route with the same velocity. So once you've gotten into that scenario, and if they're flying at the same velocity, you worry less about possible collision, and you really only have to maintain, spacing with your neighbor in front and behind. So if you look at this is a map of the Bay Area, and we have our Amazon warehouse there in Concord. If you just do a fast marching method to do shortest path from Concord to Bay Area, drop-off points, for example, and you put a cost on it. So make it very cheap to fly over water, for example. Very expensive to fly near airports, quite expensive to fly in busy urban areas, maybe a bit cheaper to fly over, less densely populated areas. Then you can quickly come up with this kind of neat route structure, which kind of looks like the air traffic control structure, right? We have these trunk highways over areas that it's very cheap to fly over because, if you're flying over water and the vehicle, something happens, it drops out of the sky for some reason, you have less chance to hurt someone in the surrounding area. And so trunk routes would then short deviations into the heavily populated areas, so minimizing the amount of time you spend in those regions. So that kind of leads to the ideas of platooning. And this is a proposal that we did for a UAV, it's like the aircraft under air traffic control. This would be a UAV under a platooning-based control. So if it's off the highway, it's kind of in a free control mode. But as soon as it gets onto the highway, it's in a platoon. It's either its own platoon, it's the leader of a platoon, or it joins a platoon, so it becomes a follower. If it's faulty, if something happens, you have altitude to work with. So typically these would be flying in an altitude, and you can use different altitudes for faulty modes. So this is our proposal with NASA. The transitions from modes, so this is a hybrid system. The transitions are basically the switching conditions that you want to generate automatically, and you can do that using reachable set calculation. So in each mode, you've got the relative dynamics of the vehicle. This is an example of a stream of vehicles which is joining a highway. So here's a highway. The red vehicle is going to come and join the highway, and then the blue vehicle is going to come and join behind it. So for each of these, we've computed the target set. Once it's in the target set, it will have a control law that basically snaps it onto a moving target on the highway, and it's avoid set. So the avoid set for the red vehicle would be anything would be computed with respect to its relative dynamics with the blue vehicle. So we're showing the projection onto the XY space here, but the models that we're using here for these computations are 5-dimensional quadrotor models in this case. And so then the blue vehicle has that same reach-avoid region with respect to its target and the red vehicle. So that's just showing the sets. But if you look at this, so if you look at the control law, now, I'm not showing the sets, but for a stream of vehicles joining a highway, you see this kind of organic motion of the vehicles. So underlying all of this, the switching from onto the highway, that's computed automatically using those reach-avoid set calculations. And so then if you have vehicles that are not following the rules, so there's a vehicle and it's detected, so it's just flying through, the vehicles have, they based on their understanding of what its dynamics are, they can quickly compute relative dynamics with respect to that vehicle and then an unsafe region. So when they first touch the boundary of that unsafe set, they depart from the highway and then rejoin again after the intruder vehicle has flown through. Okay, and so we've done these. We've also did some experiments to show these running, in the lab. These are our, okay, now we're not building our own quadrotors. Now you can buy them on every street corner. So these are these little crazy flies. And just showing the different control modes. So forming a platoon, intruder avoidance. So you can see here the vehicles, so this sort of what looks like a kind of natural avoidance, but basically they're using these reachable set calculations for the control law to avoid that intruder vehicle. And then this one is just an experiment showing the vehicles on 2 different highways and then changing highways. So using that same kind of trunk root structure that I showed previously. Okay, so that's one idea. I mean, just using that as an example of how we reduce the dimensionality of the problem by imposing practical constraints, like protocols, like highways, like platooning structures, for example. There are other things we have done which they're a little more general. I think they're a little more general because they go directly to the dynamics of the system. So suppose you had dynamics where you had a high-dimensional ordinary differential equation. You could actually try to project those dimensions down onto lower dimensional subspaces and do the computation in lower dimensional subspaces. And then the dimensions that you are not projecting, so the dimensions that have been projected away, those could be considered disturbance. That the dynamics in those dimensions could be considered disturbances with respect to the low dimensional projections. And so this is this idea of decoupling disturbances, which we worked on recently. And basically the idea here is, this is just one of the particularly interesting reachable sets for a projection where we took a 4-dimensional, just to visualize, we took a 4-dimensional system and then computed the approximate the approximate decoupling in these 3-dimensional subspaces. And so as you kind of increase the number of slices in how you represent the disturbance, so you get a finer approximation of what those disturbances are. You get this gray region represents the approximate reachable set. It comes closer and closer and closer to what the exact reachable set would look like. And this is an idea that we took a little bit further, and we asked, could you actually think of a more general theory for decomposing systems? So the idea of computing perhaps even exact reachable sets based on decompositions. And I'm going to spend a few minutes on this because I think it's maybe a little more general than we present here. We're looking at differential equations and hybrid systems, but this is an idea that we've worked on with one of our collaborators at Stanford in decomposing POM-DPs. So it's basically a structure of a representation of a transition system or a dynamic system. So the idea, and I'll introduce it kind of by means of an example like I did that last one, is that of self-contained subsystems. So suppose you have a high-dimensional system, yet it has subsystems which are self-contained, meaning that their evolution only depends on the variables within in our case, the right-hand side of the differential equation, the vector field of the differential equation. So the variables that cause that system to evolve are some subset of the entire set of state variables. And if you can basically represent those subsystems in lower dimensional spaces, then you can again do the computation in the lower dimensional spaces of those subsystems. So again, let's use this three-dimensional example. This is just a Dubin's car example for illustration. The vector field just contains these variables, the input, the velocity, the angle, and you can do a 3D calculation, and we have. But you could also break that into that three-dimensional system into two-dimensional subsystems. So I can look at the x dot theta subsystem and the y dot theta subsystem. Sure, there's overlap. You can see I've got an overlapping variable. But if you treat that overlapping variable properly, then you can actually recompute. You can compute these two lower dimensional sets and then stitch them together to get an exact representation of the higher dimensional set. So this is the idea. Break it down into subsystems, compute the separate 2D reachable sets, which is, of course, faster than doing two-dimensional, is much faster than doing a three-dimensional, and then stitch them together. Okay, so it's not really interesting for this 3 to 2. It becomes interesting when you can start doing computations in states of a dimension that you weren't able to compute directly previously. So this is a kind of illustration of that. You basically take the overall set that you're interested in 3D. You're basically projecting that set down into the two-dimensional subspaces. And then what you're asking for is a computation. So the computation in each of those subspaces. Okay, so in this we're doing a couple of things simultaneously. We've done the projection of the x, y, theta system down into the x theta and the y theta system. And then we did the computation in the, let's see if I can capture that. We did the computation in the, in parallel in the two-dimensional subspaces. Okay, so you can catch that. Okay, so then we reconstruct the original set, compare it to what you would have gotten from doing an exact computation of the three-dimensional set, and you can prove that it's exactly the same. But even for this 3D to 2D system, you get a significant speed up. So we asked, how general is this, and under what conditions can you do this self-contained subsystem decomposition more generally? So here's an example of a six-dimensional system. This is we had previously done this acrobatic quadrotor example, but we'd done a kind of artificial projection down onto lower dimensional subsystems. And this six-dimensional system can eventually be turned into two-dimensional subsystems and still capture all the dynamics. So, it's hard. When it becomes a six-dimensional set, it's kind of hard to represent the actual, you're representing the set in terms of its projections. So we're showing here, or trying to show slices over the angular, the in-plane angle of the quadrotor across the x phi space and the xy space. So it's a little hard to picture, but basically we have all that information stored. Here's a 10-dimensional system of a near-hover quadrotor, which we turned into 3 systems, 3 subsystems, 2 3-dimensional subsystems, and a 1-dimensional subsystem. And here's an example. Here it's really hard to visualize, but it's an example of a set that we couldn't have computed before with just the regular tools. Okay, and then let me finish this first bit before we move on to the last bit about learning, just by talking about a last point. This is a very recent development in dealing with the curse of dimensionality. So we can exploit offline computation to be able to use these reachable set computations online or in real time. What I've shown you so far have been kind of after-the-fact analysis type examples where we've computed this reachable set and we've either used it for control or we've used it to analyze whether or not the system is safe or what control would guarantee safety. So here we had the idea of applying it directly in planning, in robot motion planning. So in general, if you're looking at standard robot motion planners, if you want the full dimensional dynamics, the planning is slow because the dimensions are high. There's most of robot motion planning lives in this world where we have very simple planners, but it's less accurate. So you're not guaranteed that the dynamics are going to satisfy the plan. They're usually off the plan a little bit. And so typically you bloat your obstacles by some amount, and that's typically an ad hoc procedure. So what we thought is if we could calculate the model, which represents the relative model between, say, a fast and accurate planning model, like a point mass model that is used in RRT all the time, and the detailed dynamic model. So that's a relative dynamic that we can compute. And then we can compute the reachable set required to stay within a pre-specified error bound for that relative dynamics. We can pre-compute that ahead of time. It's just a relative set that moves along with the vehicle. Then we can bloat the obstacles by that computed reachable set and guarantee that our planner, even though it's computed in real time on the fast model, it will maintain the constraints with respect to the higher dimensional model. And so that's this proposal that we've put in the middle here. And so here, we're just really using reachability. Okay, so for example, we can use control and disturbance effectively here. So the fast planning system, the low dimensional, the RRT, it tries to maximize a cost, where the tracking system tries to minimize that cost. So you see that same game structure here. And here the cost represents the distance that the guaranteed distance that you want to maintain between a planning model and a higher dimensional tracking model. Okay, and so you can capture this maximum cost over time. It's just a simple reachability calculation. Okay, so here, for example, is this pre-computed tracking bound, is the reachable set for 3 different pre-specified error bounds between a tracking and between a simple planning model and a more detailed tracking model. And as this is a Dubin's car, so they look kind of interesting. There's always the ability to turn around to stay within a set. So you see that kind of dynamic behavior. But when the set gets so small, there's nothing you can do. You can't turn around anymore. So you just basically have to use that whole set. So then this is the set. Well, this is a projection of the set. These are the sets that you would use, that you would propagate around in real time with your planner. Okay, so that's what the set looks like in this Dubin's car example. And so we did this, in simulation. So here's that 10D quadrotor, which is tracking a 3D point source. We've shown the projection of that tracking error bound computed through the reachability of the error model between these two, projected onto the XYZ space. That's just a box. So this vehicle is discovering these obstacles in real time, but it's always staying within that tracking error bound because we've pre-computed that and we're planning based on that tracking error bound. And what's sort of neat about this is that you can then use that, and you can sort of think about variations on this, where you have a variety of planners. Some may be a little more detailed than others. They may use a bit higher dimensional models, so they're a bit slower. So you could have fast planners and slow planners, and use your fast planner if you're in wide open space. And then when you get to corridors where you need a little more accuracy, you can switch to a slow planner. And moreover, because of reachability, you can pre-compute where you have to be so that you can safely switch to a slower plan and stay within the bound. And so this is an example of this. Here we were flying and tracking a trajectory, and you see at this point the tracking error bound becomes smaller. The computation becomes a bit slower, but it switches over at about a point here so that it stays, so that it computes the optimal control to stay within that tracking error bound. And we have a little bit of a movie of this. Let me just show you the video of the quadrotors following this, because we flew this in the lab, and we made a video of this. Actually, let's just jump to see if we can play it from here. Okay, so here we see, we're tracking our obstacles are just these big bubbles. And you can kind of see there's two models here. There's a planning model and there's a tracking model. This is just using a linear quadratic regulator. So, we're just trying to show that, even under the typical thing you do, which is to use an LQR to track a plan, you're not guaranteed to stay within that tracking error bound. So now, if you apply reachability, and so you both have the tracking error bound and the control to keep you within that tracking error bound, you can apply this in real time. And even if your planner is kind of switching around quickly, you've computed a guarantee to keep you within a certain bound of that planned trajectory. So here you can see we don't actually have the obstacles in the lab yet, but it's the quadrotor, and it's basically mimicking, it's following the tracking-based control and, mimicking the obstacles that, they're virtual obstacles that you can see down here. Okay, so that gives you an idea about dealing with the curse of dimensionality. And in the last 10 minutes, let's talk about integrating learning into this. So I motivated this by saying that typically when you're controlling a system in a real environment, you're learning, you're gathering data about your environment, and that changes the model. It may change, so we talked about disturbances in the system, and so an understanding of those disturbances can be improved as you're running the system in real time. And so we had the idea that if you could learn about those disturbances, then you may be able to incorporate that in computing this safety bound, and you may be able to become less conservative over time. But we started with a much simpler idea, which was kind of motivated by, when you see all these training of robotic systems, and they're always like crashing into things, and then they learn not to crash by crashing. How do you actually maintain safety in a system while it's learning to perform some task? So our thought was, well, if you had a nominal model of the system where the error bound, the kind of disturbances that you would encounter are within some bound. You don't know what they are, but you know that bound. Then you can compute a safety control based on reachability for that nominal model with that bound, and then just operate in that envelope. And then as you operate, run a learning control that learns those disturbances over time. And as long as those disturbances stay within the bound that you computed the reachable set based on, then you're guaranteed that the system, as it learns, will stay within that reachable set. So we did, so that was the idea. Let me skip this and just sort of reiterate that idea. So separate the problems at first. You run a safety-based control on a nominal model, and then you improve the performance over time, but stay within the safety bounds. Okay, so here is an example. This is a quadrotor, and it's trying to track a step trajectory. And so safety here means it has to stay within a flight envelope. We don't want it to crash into the ceiling or in the floor. So in its vertical dynamics, you want its velocities to be such that when it's approaching the ceiling, it starts to slow down, or when it approaches the floor, it starts to slow down so that it doesn't crash. What we did was we had a model, and we computed that envelope using reachability, and then we took the model, for kind of a stark example, we took the model away from the vehicle. So it started out without a model of itself, and so it didn't have a control law at the beginning of the experiment, but we ran a very simple learning scheme to try to get the vehicle to learn to track this step trajectory in altitude. So it just wants to go up and down. Okay, so you start this, and what happens? So the vehicle first drops because it doesn't have a control. It's just going to drop, but it doesn't crash because when it reaches the boundary of its envelope, it has the safety-based control to keep it inside the envelope. And then it sort of bumps up and down against the bottom of that envelope, and in doing so, it learns that if it applies a little bit of thrust, it actually moves up. So after just a little bit of time, it does a fairly good job of learning what it should apply in control to track that trajectory. So you saw that was this blue dashed trajectory, and it takes about a minute. It's not doing a perfect job, basically because it can't track that trajectory perfectly and stay within the envelope. But the red here indicates where we're injecting the safety-based control. You see that when it's coming down, it's altering its velocity so it doesn't crash into the ground. Okay, so we're not changing the envelope here. We just learned the model over time, and we learned the control it should use. So now we can think about doing what we really want to do, which is being a bit less conservative. You run the system for a period of time. You learn more about the environment, about the disturbances in the system. You can use that to reduce the conservatism in your model. We used a Gaussian process representation for the disturbance function here. And the idea, we call it online disturbance model validation, is that you start with some nominal representation again for what safety means. And as we saw at the very beginning, you've got these if it's an invariant set, you have these super zero level sets that can also certify safety. So you run the system, and suppose there's a point at which you measure. So you're running the system. You've got this envelope, which is kind of bookkeeping safety. And then you measure the disturbance as you're moving along, because you're measuring you've got your own trajectory, you know the difference between the dynamics that you're experiencing and what your model is. So that gives you a representation of the disturbance. So suppose there's a point at which your disturbance model is invalidated. In this case, you get a disturbance that's outside the bound that you computed the original reachable set based on. So you're in trouble. So you can expand the reachable set to a super zero level set to the point at which that level set certifies the safety for the disturbance model you're building up via the GP, the learning of the GP, of the disturbance function. So basically what we're doing is we're computing a Bayesian prior on the existence of a usable reachable set for safety, usable level set for safety. And that computation can be done in real time. And over time, as you gather more data, you would expect that if you started with a conservative model, that conservatism would be reduced, that you would learn more about the system. But it could expand or it could shrink. Okay, so the last experiment that I'll show, actually I'll skip that one and I will really show this one. I think it's a little more effective, is showing kind of two experiments we ran in sequence, but we'll show them side by side. So this is the online model validation. We ran the quadrotor step experiment again. On the left-hand side, there's no online model validation. So there's no learning, there's no shrinking or expanding of the safety envelope. On the right-hand side, we incorporate that. Okay, so at the beginning, it's kind of boring. They're following this step trajectory as we saw before. But the thing here that we introduced is this is a big fan, and basically it produces a big wind disturbance in the lower part of our lab. So normally the vehicle would come down, the bottom of its envelope is about there, and it would just keep tracking this trajectory. So at this point in the experiment, as it kind of leaves that region of the room, we turn on the fan, which produces kind of a big wind disturbance here that was not in our original disturbance model. So it was a way to kind of starkly introduce something that gives you disturbances which are outside of the model that you started with. And so what happens as it comes down again, you see that both vehicles start to get buffeted around by the wind. In this side, what it's doing is it shrinks the envelope to a point, to a level set at which it last sees a valid disturbance function within the bound that it understands. Okay, so it just doesn't allow it to go into that region until it's explored that region a little bit more. And so on this side, it doesn't do anything, so it just gets knocked around, and it's not updating its model at all. Okay, so it's not perfect, because now we have to think about ways to be less conservative. How do we now explore that region, or start to explore that region, to ask, is it okay to venture there? Because, with the mechanism we're using, it should, if you turn that disturbance off, it should gradually start to use that part of the state space again. Okay, so that's kind of our two first steps into incorporating data-driven methods. Yeah, you could use basically any method we want. We've tried different, you saw some of the methods we're using for learning, but we've tried this using a variety of learning methods, and that's been a kind of interesting experience in itself. So let me summarize and complete the talk to say that the focus has been on so safety critical control systems with applications in air traffic and sort of local applications in robotics, in which typically the dynamics can be quite complex. So we're seeking, typically simple solutions. There's humans in the loop. We'd like the laws to be, the resulting control and automation to be understandable. But we'd also like to incorporate data-driven components. And so we talked about safety analysis using reachability, simplicity using a hybrid system representation, and the ability to learn from new information. So one set of ideas for incorporating machine learning into reachable set calculations. Just some pictures of some of the other projects we're working on. Some of them are a bit old, as you can see from the dated phones, but we're trying to collect a lot of data with human in the loop. So different ways of doing this, either through online games of landing aircraft in an air traffic control scenario to see how people tend to deal with lots of movable data. We have a game between quadrotors and people around the Berkeley campus, in which the quadrotors can help the people win a capture the flag game with the visibility that they have. And we've also, as I said, worked a lot with, and we continue to work a lot with air traffic control, thinking about really human in the loop scenarios and how you design control laws when you know that for the foreseeable future there will be a human in the loop, which is often a harder situation to deal with than a fully automated system. So with that, I'd like to conclude and thank some current students who are in bold here working on these projects, some more recent former students, and the funding agencies. Thank you very much.
Claire, and you've left time for questions. So. Any questions?
Thank you. Just asking this because you mentioned game theory. Can you elaborate a bit more about how you define the utility function and the contribution concepts?
So for most of the examples that I've shown here, the game is a two-player zero-sum differential game. And the cost is a binary cost, which we represent with a level set function as to whether or not you enter the unsafe region that we've predefined. So we have to be able to represent that region as a subset of the state space of the system. Whether or not you enter that over any course, over the time horizon, whether or not you enter and you could leave it again. We don't want that to happen. So we want a cost that records that you've entered the set or not. And then we compute typically saddle solutions to that game in the control and disturbance, and then we basically propagate the set back with those control and disturbance solutions. And so we have some research in extending this to higher than 2 players. And there's some, you have to start imposing a lot of assumptions on the system to even be able to do a 3-player differential game problem. So typically what we do is we try to decompose the problem into sets of 2-player games. And usually you need some assumptions about some spatial separation to be able to do that, or some assumptions about the kind of protocols that I was talking about as practical ways to reduce dimensionality. It could. So the question is, should we use a cooperative game model? I mean, there we're actually, in the target reaching, we're basically using a cooperative scenario. So the only time we bring in a non-cooperative game is when we are trying to capture, even in that platooning, the uncertainty, the kinds of disturbances that might be seen in a tactical sense between 2 or 3 aircraft. The cooperative game is really like a multi-objective optimization problem, which is what we're solving here. So it's kind of like a differential game embedded in that larger problem. Question?
About the last part of the presentation. So you said when a disturbance happens outside the bounds that you define, keep shrinking the safe set, like the reachable set, until you get to the set that despite that disturbance, you are safe. So it means that you are assuming that if an unknown disturbance happens, there's a subset of that reachable set that despite that...
Yep.
So it means, so if you know that knowledge, then it means that you know that a bigger bound on your disturbance. Why you start with the bigger setup?
Yeah, that's a good question. So you have to go into this computation with a sense of how much, you have some bound on what the disturbance is, which you expect to be true, but there's some leeway, and it may be outside that. If it's too far outside that bound, then there's going to be no set which validates that assumption. So you not only have to assume something about how far, for this to work, there has to be some sense of continuity of how the disturbance function interacts with those sets. But also, you have to have gone into this computation having computed enough of the function to be able to expand or shrink that, to be able to do it. Yeah. Yes?
So you talked about how to maintain stability in the presence of natural disturbances or disturbances from the airflow and so on. What if there's a malicious individual who wants to somehow bring the drone down? And is it possible? So and let's say they know what algorithms you're deploying inside the controller. Can they take down the drone, or are your algorithms?
So there's two different things here, and the answers, they're both good questions. So the reason we use game theory to begin with is so that we can treat, disturbances which are either typically in air traffic control, they're disturbances because of the environment. But, the theory was developed for malicious dogfights, and so, it allows that. It just makes the disturbance set big, and it makes that set very conservative. And it's actually nice to see, as you relax your assumptions on what the disturbance is, like not only how the set grows, but how the shape of that set changes. So that's all captured. But in the learning part, if somebody knows the algorithm that you're using for learning, they can feed you data to make you learn the wrong thing. And I think that's something that we don't spend enough time thinking about these days, and we should. So, the security of learning algorithms, just kind of training them on malicious examples is not enough. In game theory, you have this wonderful result that, as the disturbance grows, you have a mathematical understanding of how the set changes. In deep networks, there's not a sense of that. So, and I think we need that if we're going to use these in safety critical systems in everyday life. So I think it's a big problem of using, if somebody knows what learning algorithm you're using, they can start to upset your data in a way that is very disruptive to your overall system.
You assume you have complete observability, so you know the state of the system you're in. What happens? And then you mentioned something that you work with POMDP, so with partial observability. How does it partial observability when you have sensing information?
Yeah, so there it's a good question. So we used what we did there was we looked at the structure of the dynamics there, the discrete dynamics, and showed that the same kind of decomposition that we had with like the continuous ODEs works for the discrete dynamics. And our collaborator at Stanford is somebody, Michael Kokendorfer, who's worked on a collision avoidance system for the FAA, and so he's used this decomposition of the Markov decision process to be able to basically deal with the multiple state dimensions and the high dimensional state space. For the partially observable part, that's separate. And so we have been assuming full observability in the problems we've looked at so far. For partial observability, we have some ideas about how to go forward, but that's definitely not a solved problem. And it's done, I'd say that in some cases it's done in a very ad hoc way, and we'd like to basically understand how we, without sort of doubling the dimension of the problem, how we have a good maintenance of a belief state in the system, that is a good representation of the current state. So the partial observability is not something that we've dealt with.
Let's have one more question then.
Maybe I can finish off with a broad question. So, are there any lessons with these methods for the continuously evolving world of autonomous vehicles and where sensing is also part of the, I guess that relates to observability as well. But any lessons there? Because
yeah, I think that the biggest question with autonomous vehicles now is models. So we have good models of cars and how they move. We don't really have good models yet of how people will react, drivers will react in given situations. And so the biggest part here is, and I think this is also something I'm very interested in, but it's how to develop models of how people interact with these systems so that we can develop, if not perfect, but good models of car motion in different scenarios. And then, obviously the worst case scenario is something that we probably wouldn't get anywhere with here, because the worst case would be collision in all cases. So how do we, I think these are very good open questions. How do we then take this idea of kind of using this function as a way to bookkeep safety, probably, taking it as once we propose a model, it becomes something that's, a model-based tool that we can then use to evaluate different control policies in autonomous cars. So we have a project at Berkeley that I'm involved in. It's run by Trevor Darrell, who's somebody who works in deep learning, and he's developed this program called Deep Drive, where one of the companies that's involved has dash cams on a whole bunch of cars, and we're getting the data for that. Now that's limited, but it's a start to be able to get build up some models that we then might integrate with safety. But that's a big project to even get started now.
Okay, let's thank the speaker once more.
Thank you.